Right now, the universe is 13.8 billion years old, and by the standards of cosmic time, it has approximately 100 trillion years left. This is not a short time. It is, by every metric we can apply, an interval so long that no human language has the words to make it meaningful. It is many orders of magnitude longer than the current age of the universe. It is many orders of magnitude longer than the duration of any biological process we know. But it is finite. By current best understanding, the universe has a finite future. How that future will unfold exactly is one of the more interesting questions in modern cosmology. There are several scenarios. Each is based on extrapolating our current physical theories far into the future. Each has its own particular timeline, its own particular sequence of events, its own particular endpoint. Tonight we are going to walk through these scenarios. You do not need to hold every number. Some you will. That is enough. The end of the universe is, in cosmic terms, very far away. It does not threaten anything we know. It is, in some sense, the long, quiet outcome of the physics that governs the cosmos. We have a couple of hours. If you have come here to rest, let this carry you. The end of the universe is, in cosmic terms, very far away. It does not threaten anything we know. It is, in some sense, the long, quiet outcome of the physics that governs the cosmos. Now, let us pull back. Let us look at what we currently know about the universe's history and trajectory. The universe began, by current best understanding, in a hot, dense state approximately 13.8 billion years ago. This is the Big Bang. The Big Bang is not, as is sometimes imagined, an explosion in some pre-existing space. It is the beginning of the expansion of space itself, from a state of extreme density and temperature. In the first fractions of a second, the universe underwent inflation. During inflation, the size of the observable universe grew by a factor of perhaps 10 to the 25 in a tiny fraction of a second. The inflation, by current understanding, set up the initial conditions for the subsequent cosmic evolution. After inflation ended, the universe entered the radiation era. Most of the energy was in the form of radiation. The universe was hot, dense, and rapidly expanding. As it expanded, it cooled. The cooling allowed various physical processes to occur in sequence. Approximately 3 minutes after the Big Bang, the temperature had dropped enough for primordial nucleosynthesis to occur. The first atomic nuclei formed, primarily hydrogen and helium, with traces of lithium. Approximately 380,000 years after the Big Bang, the temperature had dropped to a few thousand Kelvin. Electrons and atomic nuclei combined to form neutral atoms, a process called recombination. The radiation that had been scattering off free electrons was now free to propagate. This radiation, redshifted by the subsequent expansion, is what we now observe as the cosmic microwave background. Approximately 150 million years after the Big Bang, the first stars began to form. They were massive, short-lived, and metal-free. They produced the first heavy elements in their cores and ejected them when they exploded as supernovae. Approximately a billion years after the Big Bang, the first galaxies began to assemble. They grew by accreting gas and by merging with other proto-galaxies. By a few billion years after the Big Bang, the universe contained recognizable galaxies organized in a cosmic web of filaments and voids. Approximately 9 billion years after the Big Bang, our own solar system formed. The Sun coalesced from a gas cloud in a quiet arm of the Milky Way. The planets accreted from a disk around the young Sun. The Earth, in its current rocky form, was assembled. Approximately 10 billion years after the Big Bang, life began on Earth. Single-celled organisms appeared in the early oceans. Approximately 13.5 billion years after the Big Bang, complex life emerged. The Cambrian explosion produced multicellular organisms with hard parts. Subsequent evolution produced fishes, amphibians, reptiles, and mammals. Approximately 13.8 billion years after the Big Bang, we are sitting here, listening to this story. This is the history of the universe so far, in broad outline. The future will continue from this point. Now let me bring this closer. The future of the universe depends, in critical ways, on the nature of dark energy. Dark energy is the unknown component that drives the accelerating expansion of the universe. It currently accounts for roughly 70% of the total energy density of the cosmos. Its effects on the expansion become increasingly dominant as the universe ages. We do not know what dark energy is. We know it exists by its observational effects. We know its current density. We know roughly how it has affected the expansion over the past few billion years. We do not know its underlying nature, or whether it is constant or evolving. If dark energy is what physicists call a cosmological constant, with a constant energy density throughout cosmic history, then the universe will continue to expand at an accelerating rate indefinitely. The galaxies will recede from each other faster and faster. The cosmic horizon, the maximum distance from which signals can reach us, will shrink as more and more of the cosmos accelerates away. If dark energy is something more exotic, the future could be different. If dark energy weakens over time, the expansion might slow and possibly even reverse. If dark energy strengthens over time, the expansion could accelerate even more dramatically, eventually tearing the cosmos apart. These different possibilities lead to different end-state scenarios. The most widely accepted scenario, given current observational evidence, is the heat-death scenario. Let me walk through it. The heat-death scenario, also called the Big Freeze, assumes that the universe continues to expand at an accelerating rate, with dark energy behaving as a cosmological constant. In this scenario, the universe gradually cools as it expands. Matter spreads out, stars run out of fuel, galaxies move apart. The first phase of this scenario is what is called the stelliferous era. We are currently in this phase. Stars are forming, stars are shining, galaxies are active. The stelliferous era will continue for a long time, but not forever. Eventually, the gas that fuels star formation will be exhausted. New stars will stop forming. The existing stars will burn through their fuel and die. By approximately 100 trillion years from now, the last stars will have stopped fusing hydrogen. The stelliferous era will end. Stay with me here. After the stelliferous era, the universe enters what is called the degenerate era. In this phase, the most common objects are stellar remnants, white dwarfs, neutron stars, and black holes. Stellar processes have ceased. The universe is no longer producing light at the rates it once did. The white dwarfs, which are the most common type of stellar remnant, gradually cool over very long timescales. Over trillions of years, they radiate away their residual heat. Eventually, they become black dwarfs, cold and dark. The neutron stars also cool. They are even more dense than white dwarfs, with most of their material in the form of degenerate neutrons. They cool more slowly than white dwarfs, but eventually they too reach near absolute zero temperatures. The black holes do not cool in the same sense. They emit Hawking radiation, a thermal emission predicted by quantum field theory in curved spacetime. The rate of emission depends on the black hole's mass. Smaller black holes emit faster than larger ones. Over the course of the degenerate era, the white dwarfs and neutron stars cool, the black holes slowly evaporate, and the gas reservoirs continue to be depleted. By approximately 10 to the 33 years from now, the degenerate era is in its later stages. Now let me walk to the next phase. After the degenerate era, the universe enters what is called the black hole era. In this phase, the dominant objects are the surviving black holes. The white dwarfs and neutron stars have, by various processes including proton decay, if it occurs, and quantum tunneling, gradually disappeared. The black holes, by Hawking radiation, slowly evaporate. The timescale for evaporation depends on the mass. A stellar mass black hole, around 10 solar masses, evaporates in approximately 10 to the 67th years. A supermassive black hole, around 1 billion solar masses, evaporates in approximately 10 to the 100th years. The evaporation is asymptotic. The black hole shrinks. As it shrinks, it gets hotter. The hotter it gets, the faster it emits radiation. The acceleration of the evaporation produces a final flash as the black hole disappears completely. By the end of the black hole era, the last black holes have evaporated. The universe contains only the leftover radiation and a few particles drifting in increasingly empty space. This is the late phase. The cosmic landscape by this time is one of vast emptiness. The universe has expanded so much that the once dense matter is spread across volumes so large that interactions between particles are essentially impossible. The temperature, having been decreasing throughout cosmic history, approaches absolute zero. Hold this. This is, in some sense, the long arc of the heat-death scenario. The universe gradually winds down. Stars die, black holes evaporate, matter spreads out. The temperature approaches zero. The universe does not end suddenly. It does not collapse. It does not explode. It simply slowly cools. The entropy of the cosmos approaches its maximum. No further evolution is possible. This is heat death. The timescale is, by any human metric, unimaginably long. By approximately 10 to the 100th years from now, the cosmos has entered its late state. The stelliferous era ended trillions of years ago. The degenerate era ended much longer ago. The black hole era is concluding. What remains is empty space, with occasional drifting particles, slowly approaching equilibrium. That is, in some sense, what the heat death scenario predicts. Stay with me here, let me hold the cosmic timeline a bit longer. The phases we are discussing, stelliferous, degenerate, black hole, dark, have specific characteristics that are worth considering. The stelliferous era contains the bulk of the activity we are familiar with. Stars are the dominant source of energy. They convert hydrogen to helium and heavier elements. They produce light. They produce nuclear synthesis. They produce the elements that make up planets and life. The stelliferous era began about a few 100 million years after the Big Bang, when the first stars formed. It will continue for another 100 trillion years or so, by current best estimates, until the gas reservoirs are exhausted and no new stars can form. During this era, the cosmos goes through several subphases. The earliest subphase was dominated by massive population 3 Toi. Adnasarinotimori stars, the first generation, with no metals. The next subphase saw the formation of the first galaxies. The current subphase is dominated by older stars and slower star formation. The next subphase, in trillions of years, will be dominated by red dwarfs which have very long lifetimes. By the very end of the stelliferous era, only the longest-lived stars, red dwarfs and possibly some white dwarf companions, will remain. Eventually, even they will exhaust their fuel. After the stelliferous era, we enter the degenerate era. This phase, lasting from about 10 to the 14th to 10 to the 34th years, is dominated by stellar remnants. The cosmos is dim. The remaining objects are mostly cold or cooling. Various long-term processes occur during the degenerate era. Stars sometimes encounter each other through gravitational interactions, leading to mergers or scatterings. Galaxies dissolve over very long timescales. Proton decay, if it occurs, gradually depletes the inventory of stable matter. These processes are extraordinarily slow on human scales, but over the trillions of years of the degenerate era, they accumulate. The black hole era follows, lasting from 10 to the 34th to 10 to the 100th years. During this phase, the dominant objects are black holes. They have, through various processes, absorbed most of the other matter. Their evaporation is the main long-term dynamic. By the end of the black hole era, even the supermassive black holes have evaporated. The cosmos is essentially empty, with only diffuse radiation and a few drifting particles. Let me hold what the very late cosmos would look like. At 10 to the 100th years from now, in the very late phases of cosmic history, the cosmos is, in some sense, a vast empty place. The space between particles is enormous, the density is incredibly low, the temperature is approaching absolute zero. No structures of any consequence remain. If we imagine the cosmos at this time, we see mostly empty space. The occasional particle drifts through, with no interaction with any other particle for vast spans of cosmic time. The cosmic microwave background, redshifted by the long history of expansion, has reached a temperature so low that it is no longer detectable in any practical sense. The cosmos has in some sense settled into its eternal end state. No further evolution occurs, no further activity is possible. The cosmos simply is, in this state, indefinitely. This is the heat death. This is the long, quiet, eternal end. Then comes the dark era, the final phase. The cosmos is, in any meaningful sense, dead. The universe has reached its end state, with maximum entropy, and no further evolution possible. Now let me walk through the alternative scenarios. The second scenario, the Big Rip, assumes that dark energy is not a simple cosmological constant, but something more exotic. Specifically, if dark energy is what physicists call phantom energy, with an equation of state parameter W less than -1, the energy density grows over time, rather than remaining constant or decreasing. If this is the case, the expansion accelerates more dramatically over time. The acceleration eventually exceeds the gravitational binding of cosmic structures. In the Big Rip scenario, the timeline of structural disintegration is in order. First, galaxy clusters are torn apart. The galaxies in clusters, currently held together by gravity, are accelerated away from each other as the expansion overcomes their mutual binding. Then, individual galaxies are torn apart. The stars in a galaxy, held in orbits by gravity, are pulled away from each other. Then, planetary systems are torn apart. The planets, in orbits around their stars, are accelerated away. Then, planets themselves are torn apart. The gravitational binding of a planet is overcome by the expanding space. Then, individual atoms are torn apart. The electromagnetic binding of electrons to nuclei is overcome. Then, even the nuclei are torn apart. The strong nuclear force which binds protons and neutrons is overcome. The Big Rip, in this scenario, ends with the universe in a state where no structures of any kind can exist. The expansion has become so extreme that even quantum mechanical bound states cannot persist. The timeline for the Big Rip depends on the specific value of the dark energy parameter. If the parameter is close to -1, the Big Rip is far in the future, possibly tens of billions of years. If the parameter is significantly less than -1, the Big Rip could be in tens of billions of years or even sooner. Current observations do not strongly favour the Big Rip scenario. The data is consistent with dark energy being a cosmological constant, with W equal to -1. But the data is also consistent with small deviations, including the possibility of phantom energy. The matter is not settled. Let me hold this. The Big Rip, if it occurs, would be a very different end than heat death. Instead of slow cooling, the universe would experience increasing acceleration, culminating in the disintegration of all structures. The end state of the Big Rip is, in some sense, similar to heat death, in that no structures remain. But the path to that end state is dramatically different. The Big Rip is, in some sense, an active, dynamic end. The heat death is a slow, quiet end. We do not, at present, know which is correct. We continue to investigate. Now let me walk through the third scenario. The third scenario is vacuum decay. This is, in some sense, the most exotic of the major end-state scenarios. It depends on a particular feature of quantum field theory. In quantum field theory, the vacuum state, the state of lowest energy, may not be unique. There may be multiple possible vacuum states, each corresponding to different physical conditions. If our universe sits in a false vacuum, a metastable state that is not the true minimum energy, the vacuum can, in principle, decay to a lower energy state. The decay would occur via quantum tunneling. A bubble of true vacuum would form somewhere in space. The bubble would expand at the speed of light. Inside the bubble, the laws of physics would be different from outside. The change in physics would mean that the matter inside the bubble could not maintain its current configuration. Everything inside would, in some sense, be destroyed. The bubble of true vacuum would continue to expand. As it expanded, it would consume more and more of the false vacuum universe. Eventually, the entire observable universe would be inside the true vacuum bubble. This is vacuum decay. The probability of vacuum decay depends on the specific properties of the underlying field theory. For our universe, the relevant theory is the standard model of particle physics. The Higgs boson, discovered in 2012, has properties that determine the structure of the electroweak vacuum. Calculations based on the measured Higgs mass and other standard model parameters suggest that our vacuum is, in some sense, metastable. It is not absolutely stable. It could, in principle, decay. But the timescale for decay is, by current calculations, extremely long. Estimates for the vacuum decay timescale range from about 10 to the 100th years to 10 to the 700th years. The range is large because the calculation is sensitive to small uncertainties in the input parameters. What these timescales mean is that, in the unlikely event vacuum decay is relevant, it occurs on cosmic timescales that exceed even the heat death scenario. The universe, by current calculations, is unlikely to experience vacuum decay before heat death takes over. But the calculations are not certain. New physics could shift the timescales. Direct observation of vacuum decay is essentially impossible until it happens. The bubble travels at the speed of light, so we cannot see it coming. let me hold one more aspect of the deep future. The cosmos, in the very late phases, becomes a place where the standard physical structures cannot persist. No stars, no active galaxies, no biological systems, just diffuse particles and radiation slowly approaching equilibrium. In this state, the concept of time itself becomes strange. There are no processes occurring on any human timescale. The cosmos is, in some sense, in a state where time has no observable consequences. Nothing happens. Nothing changes. This is the thermodynamic equilibrium state. It is the natural endpoint of any closed thermodynamic system. The cosmos reaches it after the long winding down. Whether the equilibrium is final, or whether some new physics intervenes, we do not know. The far future is, in some sense, beyond our direct knowledge. We can only extrapolate from current physics. The extrapolation gives equilibrium. The extrapolation may, of course, be wrong. But for our current best understanding, the equilibrium is the destination. The cosmos winds down. The cosmos reaches its end state. The end state is, in some sense, eternal. No further evolution occurs. This is what current physics suggests for the very deep future. What lies beyond this, if anything, is unknown. So vacuum decay is, in current understanding, a possibility, but a remote one. It is unlikely to be the actual end state of our universe, but it is, in principle, a way the universe could end. Stay with me here. Now, let me walk through the fourth scenario. This one is, in some sense, historically important but currently disfavored. The fourth scenario is the Big Crunch. This was, for much of the 20th century, considered a plausible end state. In the Big Crunch scenario, the gravitational attraction of all matter in the universe eventually overcomes the cosmic expansion. The expansion slows, stops, and reverses. The universe then collapses inward, with all matter falling toward a final singularity. This scenario would be, in some sense, the time reversal of the Big Bang. The cosmos would compress back into a hot, dense state. Galaxies would merge, the temperature would rise, the end state would be a singularity, similar in some ways to the initial state of the universe. For the Big Crunch to occur, the total density of the universe would need to be greater than a certain critical value. Specifically, the average matter density would need to exceed the threshold for gravitational closure. Current observations strongly suggest that the universe is not closed in this sense. The expansion is accelerating, not slowing. The dark energy that drives the acceleration would, by current models, prevent any future collapse. So the Big Crunch is, given current evidence, not the likely end. It remains a theoretical possibility under various exotic assumptions about dark energy, but it is not favoured by the data. I mention it for completeness. It was, historically, one of the major candidates for cosmic fate. It has largely been replaced in modern cosmological thinking by the heat-death scenario as the most likely outcome. Hold this. Let me sit with what these scenarios mean, considered together. We have four possible cosmic fates. Heat-death, most likely. Big Rip, possible if dark energy is phantom. Vacuum decay, possible but unlikely in any reasonable timescale. Big Crunch, currently disfavored. The most likely outcome is heat death. The cosmos continues to expand, gradually cools, gradually empties out, and ends in a state of maximum entropy with minimal activity. Each of the other scenarios has its own particular form of ending. The Big Rip is dramatic. The vacuum decay is sudden. The Big Crunch is collapse. Let me hold what makes each scenario distinct, in addition to the differences I have already drawn out. Heat death is, in some sense, the natural extrapolation of current physics without any new ingredients. If our current understanding of the cosmos is broadly correct, and if no new physics intervenes, heat death is what we should expect. It is in this sense the default scenario. The Big Rip requires additional physics beyond what we currently observe. Specifically, it requires dark energy to be phantom in nature, with an equation of state parameter less than -1. Such physics is not strongly motivated by current theory, but it is not strongly excluded either. It is, in this sense, a possibility that depends on specific assumptions about dark energy. Vacuum decay requires that our quantum vacuum be metastable, with a lower energy true vacuum accessible by quantum tunneling. The calculations based on the standard model parameters suggest this is the case, but the timescale is so long that it is unlikely to be relevant for any practical purposes. The scenario depends on details of quantum field theory that are still being explored. The Big Crunch requires that gravity overcome dark energy at some future time, leading to a reversal of cosmic expansion. Current observations strongly disfavor this scenario. Dark energy has been driving acceleration, and there is no sign of the acceleration weakening. The Big Crunch would require some new physics that makes dark energy ineffective in the future. Each of these scenarios has its own set of physical assumptions. Heat death requires the fewest, beyond current understanding. The others require progressively more speculative assumptions. This is one of the reasons heat death is favoured. It is the most economical extrapolation. The alternatives, while not impossible, require additional ingredients that are themselves speculative. But in all four scenarios, the universe has a finite future. None of them ends in a steady-state continuation of the current cosmos. The cosmos, by current understanding, has a trajectory towards some kind of end. Let me hold the contrast between heat death and Big Rip a little longer. The two scenarios produce, in some sense, opposite kinds of ends. Heat death is slow, gradual, asymptotic. The cosmos winds down, cools, empties, approaches equilibrium. Nothing happens suddenly. The Big Rip, by contrast, is dramatic. The cosmos is torn apart. The expansion accelerates without bound. Structures, from galaxies down to atoms and possibly nuclei, are disintegrated. The end is rapid. The two scenarios reflect fundamentally different behaviours of dark energy. Cosmological constant dark energy gives heat death. Phantom dark energy gives the Big Rip. The observational difference between these two is, at present, subtle. Both predict an accelerating expansion. Both are broadly consistent with current data. The difference would become apparent only over much longer timescales than we have observed. This is one of the challenges of cosmic fate prediction. The differences between scenarios are, in some sense, in the deep future. We cannot, by direct observation, see the future. We can only test our current models for consistency with present data and extrapolate. The extrapolation gives, for our current best models, heat death as the most likely outcome. But the alternative, Big Rip, cannot be definitively ruled out. We continue to refine the observations. The DESI survey, the Vera Rubin Observatory, and other ongoing programs will, in the next decade or so, give us better constraints on dark energy. The constraints may eventually distinguish heat death from Big Rip. What kind of end, we do not yet know with certainty. We have a leading candidate, heat death, and several alternatives. The leading candidate is consistent with current observations. The alternatives require modifications to our current best theories. Now let me bring this closer. The timescales for these scenarios are, as I have indicated, all extremely long. Even the soonest possible Big Rip would be tens of billions of years from now. Heat death plays out over trillions of years. Vacuum decay is even further in the future. These timescales are, in any meaningful sense, beyond any biological scale we can imagine. No species, no civilization, no observer of the kind we currently are will be around to witness any of these scenarios unfold. The end of the universe is, in some sense, far beyond our experiential horizon. This is a striking realization. We are doing cosmology in the very early stages of cosmic history. The cosmos is, in some sense, just getting started by its own standards. We are, in this picture, the equivalent of cosmic infants, looking ahead at a vast future we cannot experience. But we can model, we can extrapolate, we can think about what will happen, even if we cannot see it. This is in some sense what cosmology gives us. Access to the deep future of the cosmos through the application of physical theories we have developed and tested. The access is partial, the future is uncertain. The various scenarios cannot be definitively distinguished without observations we cannot yet make. But the access is real. We can, in some meaningful sense, see into the deep cosmic future. Stay with me here. Now let me walk through the most likely scenario, the heat death, in more detail, because this scenario has been worked out in some depth. The heat death scenario, as I have described, involves the cosmos gradually winding down. The stelliferous era ends with the last stars dying. The degenerate era is dominated by stellar remnants. The black hole era is dominated by black holes slowly evaporating. The dark era is the final phase, with only diffuse radiation and occasional particles. Each phase has its own timescale and its own characteristic processes. The stelliferous era continues until approximately 10 to the 14th years from now. During this time, stars form and die. The total mass in stars gradually decreases as more material is locked up in dim or dead remnants. Eventually, the gas reservoirs are exhausted, and no new stars can form. The existing stars burn through their fuel. By 10 to the 14th years, the last main sequence stars have left the main sequence. The cosmos is populated by stellar remnants, white dwarfs, neutron stars, and black holes. Some active stellar phenomena continue, but the bright phase of cosmic history is over. The degenerate era extends from approximately 10 to the 14th years to approximately 10 to the 34th years. During this phase, the stellar remnants cool. White dwarfs gradually radiate away their stored heat. Neutron stars do the same, more slowly. Various dynamical processes scatter stars out of galaxies, ejecting them into intergalactic space. By the end of the degenerate era, the cosmos is in a more dispersed state. The galaxies have, in some sense, dissolved. The stellar remnants have spread out. Various long-term processes, including possibly proton decay, if it occurs, have begun to deplete the inventory of baryonic matter. The black hole era extends from approximately 10 to the 34th years to approximately 10 to the 100th years. During this phase, black holes are the dominant gravitating objects. They have absorbed most of the other matter through various processes. Their evaporation is the main long-term dynamic. Black hole evaporation, as I mentioned, is faster for smaller black holes. The smallest black holes evaporate first. The supermassive black holes are the last to go. By the end of the black hole era, the last supermassive black holes have evaporated, releasing their mass back into radiation. The dark era extends from 10 to the 100th years onward. During this phase, there is nothing left except diffuse radiation and occasional drifting particles. The temperature approaches absolute zero. The cosmos is, in some sense, dead in the thermodynamic sense. This is the projected sequence. It is based on extrapolations of current physics far into the future. Each phase involves assumptions that may or may not turn out to be correct. But the broad picture is what current theory predicts. Let me hold this picture for a moment. The cosmos has, in some sense, a particular life cycle. It is born in the Big Bang. It goes through the stelliferous era, during which stars form, shine, and die. It enters the degenerate era, with cooling stellar remnants. It enters the black hole era, with evaporating black holes. It enters the dark era, with diffuse radiation only. The total span of the life cycle is, by current best understanding, dominated by the dark era. The bright phase, the stelliferous era, is, in cosmic terms, brief. The current age of 13.8 billion years is, in some sense, near the early end of the stelliferous era. The vast majority of cosmic time, even within just the stelliferous era, lies ahead. So we are, in some sense, in the early evening of cosmic history. There is much yet to come. Stay with me here. Let me also walk through the question of how dark energy might evolve over time, because the nature of dark energy is, in some sense, what most directly determines the cosmic fate. Dark energy, as currently measured, has an equation of state parameter UW very close to -1. The exact value is uncertain. Different observations give slightly different values, with error bars that overlap with W equals -1. If W is exactly -1, dark energy is a cosmological constant. The energy density remains constant throughout cosmic history. The universe expands at a rate that approaches an exponential law over time. Heat death is the outcome. If W is slightly greater than -1, dark energy is sometimes called quintessence. The energy density decreases slowly over time. The universe still expands, but at a slowly decreasing rate. Heat death is still likely, but on potentially different timescales. If W is slightly less than -1, dark energy is phantom energy. The energy density increases over time. The expansion accelerates faster and faster. The Big Rip becomes possible. Current best observations give W in the range of -1.0 plus or minus about 0.1. The data is most consistent with a cosmological constant, but slightly evolving dark energy is also possible. Phantom energy is not strongly favoured, but it cannot be ruled out. The DC survey, ongoing since 2021, has begun to provide tighter constraints on dark energy evolution. Initial results from 2024 hinted at modest evolution. Subsequent data releases will refine the picture. If dark energy is, in fact, evolving, even slightly, our cosmic fate could be different from what the simple cosmological constant model predicts. The Big Rip might be reachable in tens of billions of years, or it might be permanently out of reach. The matter is being constrained by ongoing observations. For now, the consensus is that heat death is the most likely outcome, but the alternatives are being investigated. Now let me sit with the philosophy of all of this. The end of the universe is, in some sense, the deepest cosmological question we can ask. What ultimately happens to the cosmos? The question has been asked, in various forms, throughout human history. The various religious and philosophical traditions have given their own answers. Modern cosmology gives a particular kind of answer. The answer is based on physics. It assumes that the laws we have learned will continue to apply far into the future. It extrapolates from current observations to predict future states. The answer by this method is heat death. The universe will gradually cool. Stars will die. Black holes will evaporate. The cosmos will end in a state of maximum entropy. This is not, of course, a comforting answer for everyone. The thought that the universe has a finite future, that all activity eventually ceases, that the cosmos winds down into nothingness, is, for many people, disturbing. But it is the answer that current physics gives. The answer rests on the assumption that the physics we know will continue to apply. If the physics changes, if there is new physics in the far future that we have not yet discovered, the answer could be different. We do not at present have evidence of such new physics. The current theories work. The extrapolations to the deep future are, by current understanding, the best we can do. Let me hold one more thread before we continue. The work on cosmic fate is, in some sense, the work of extending our understanding to the limits of what is possible. We are taking our best current physical theories and applying them to extreme regimes, the very far future, the very low temperatures, the very long timescales. This is in some sense the kind of work that pushes the boundaries of physics itself. By asking what happens to the cosmos in the deep future, we are testing how well our theories handle conditions far beyond anything we can directly observe. The tests are theoretical rather than experimental. We cannot, in any practical sense, verify the predictions about the far future. But the theoretical work is still valuable. It clarifies the implications of our theories. It identifies the parameters that matter. It points to the observational tests that, in principle, could distinguish between scenarios. The work has, over the past several decades, given us a clearer picture of what current physics says about cosmic fate. The picture is, broadly, the one I have walked through. Heat death is the most likely outcome. Other scenarios are possibilities. The timescales are vast. This is what we know. This is what we have built up through the work of generations of physicists and cosmologists. The picture is not complete. It will presumably be refined over time, but it is what we have so far. Tonight we have walked through this picture. We have considered its details. We have considered its implications. The picture is, in some sense, what we have done with our best tools for thinking about cosmic fate. Let me hold also the question of how the picture might be wrong. Our extrapolations to the deep future depend on assumptions about physics that we cannot, in any practical sense, verify directly. The extrapolations are based on theories that have been tested for the current and recent eras. The application to the deep future is, in some sense, an extension beyond the tested regime. The possibility that the physics changes in the deep future is real. New phenomena could emerge. The fundamental constants could, in principle, evolve. New particles could become relevant. The standard model itself could need extension. If any of these things happen, the picture of cosmic fate could be different from what we currently predict. Heat death might not be the final state. New phenomena might preserve some activity in the cosmos for much longer than current models predict. We do not know if any of this is the case. We have no direct evidence for it. But we cannot rule it out. This is, in some sense, the limit of cosmic fate predictions. We extend our current physics as far as we can. The extension gives us a picture. The picture may be incomplete or wrong in ways we cannot at present detect. The work, however, is still valuable. Even if our predictions are eventually superseded by better theories, the current predictions represent our best current understanding. They are the framework on which future refinements will build. So we have, in some sense, what current physics allows. The picture is, by current best understanding, heat death over vast timescales. Future revisions to the physics might change this. We continue to investigate. The heat death scenario is, in this sense, our best current guess about the cosmic fate. Let me also walk through one more aspect of the heat death scenario, which is the question of what it means for the cosmos to reach its final equilibrium state. The thermodynamic concept of equilibrium is, in some sense, what defines heat death. The cosmos reaches a state where no further processes can occur because there are no gradients to drive them. The temperature is uniform, the matter is dispersed, the energy is distributed. This is the maximum entropy state of the cosmos. It is the state of greatest disorder. It is, by the second law of thermodynamics, the natural endpoint of any closed thermodynamic system. The cosmos as a whole is treated in this analysis as a closed system. Energy is conserved. Entropy increases. Over time, the system approaches its maximum entropy state. This is a powerful framework. It connects cosmic fate to one of the deepest principles of physics. The second law, which has been verified across countless experimental tests, applies to the cosmos as well as to laboratory systems. The application of the second law to the cosmos has been worked out in detail. The entropy of the early universe was, by careful analysis, surprisingly low. The entropy has been increasing since. The maximum entropy state is, in some sense, the natural destination. This is why heat death is the favoured scenario. It is consistent with the most fundamental physics we know. It is the expected outcome of the universe's thermodynamic evolution. Whether the second law continues to apply in the very late universe, or whether some new physics changes the picture, is a question for future research. For now, the second law, applied to the cosmos, suggests heat death. Let me also walk through the implications for cosmic information. The information content of the cosmos, in some sense, evolves over time. The cosmos starts in a low entropy state, with limited information. Over time, as processes occur, the entropy increases. The information distribution changes. By the end of the heat death scenario, the cosmos has reached maximum entropy. The information is, in some sense, fully distributed. There are no gradients, no organized structures, no patterns. The information is, by this measure, dispersed but maximally diluted. This is the thermodynamic endpoint. The cosmos has reached its final state. No further information processing is possible. From the perspective of the cosmos as an information processor, the heat death is the cessation of activity. No new patterns can form. No old patterns can be preserved. The cosmos becomes, in some sense, informationally inert. This thermodynamic perspective has been one of the more philosophically discussed aspects of cosmic fate. The idea that the cosmos has a finite information processing capacity, that it will eventually exhaust this capacity, has been considered by various thinkers throughout the past century. Different thinkers have responded differently. Some argue that the finite capacity is, in itself, meaningful. We have our time within the cosmic information processing window. Others argue that the eventual cessation undermines any deeper meaning. These are philosophical questions. The physics gives us the prediction. Heat death. The interpretation is up to us. It is, in some sense, a humbling conclusion. The cosmos that we inhabit, that has produced us, that contains everything we know, will eventually end. Not violently, not dramatically, but quietly, gradually, in a long, slow winding down. This is what current physics suggests. Let me also walk through what vacuum decay would look like in detail, because the scenario, while unlikely, is conceptually fascinating. Vacuum decay would occur if our quantum vacuum is metastable, if there is a lower energy vacuum state available. The decay would proceed by quantum tunneling. Somewhere in space, a small bubble of true vacuum would form. The bubble would have lower energy density than the surrounding false vacuum. By energetic considerations, the bubble would be stable. It would, in fact, want to grow. The bubble would expand at the speed of light. Inside the bubble, the laws of physics would be different from outside. The differences would, in general, mean that the matter inside the bubble could not maintain its current configuration. Atoms, molecules, fundamental particles, all would be reconfigured in ways that depend on the specific physics of the new vacuum. The bubble would continue to expand, indefinitely. Any matter it encounters would be transformed into the new vacuum's version of physics. Any signals being emitted by the doomed matter would, of course, also be subject to the new physics. For an observer outside the bubble appears to be expanding at the speed of light. The observer cannot detect the bubble before it arrives. The bubble's leading edge moves at the same speed as any electromagnetic signal it might emit. So the observer is, in a real sense, instantaneously transformed when the bubble reaches them. This is what makes vacuum decay so dramatic. Unlike heat death, which involves slow, gradual change, vacuum decay would be sudden. From any observer's perspective, one moment they are in the false vacuum, the next they have been transformed into the true vacuum, whatever that means. The transformation, presumably, would destroy any structures that depend on the specific properties of the false vacuum. Atoms, as we know them, would cease to exist. Any complex chemical structures would be disrupted. The light we see, the heat we feel, the matter we are made of, all dependent on the current vacuum state. What replaces them in the true vacuum is not, in general, predictable. The new physics could be radically different. The new physics might not support complex structures at all. The new physics might, in some scenarios, allow for stranger forms of existence that we cannot anticipate. This is the picture. Vacuum decay would be, in some sense, an immediate cosmic transformation. It would happen when it happens at the speed of light. There would be no warning. There would be no escape. But, as I have said, the timescale for vacuum decay is, by current calculations, extraordinarily long. The probability of vacuum decay during any time interval comparable to cosmic timescales is, by current estimates, extremely small. The vacuum decay scenario is, in this sense, more of a theoretical possibility than a practical concern. It is, in some sense, the most dramatic but also the most remote of the cosmic fate scenarios. Now let me bring this closer. I want to walk through some of the implications of heat death for our own situation. First, the timescale is vast. By any human standard, heat death is unimaginably far in the future. The age of the cosmos so far is 13.8 billion years. Heat death is, by best estimates, 10 to the 100th years away. That is a number with 100 zeros after the 1. It is in some sense no longer comparable to any human scale. So in any practical sense, heat death is not relevant to us. We will not experience it. Our species will not experience it. Even our cosmic environment, in any recognizable form, will not exist for most of the time before heat death. Let me hold this point. The cosmic timescale of heat death is so long that it dwarfs every familiar reference. The age of the cosmos so far is 13.8 billion years. Heat death is 10 to the 100th years away. The ratio is 10 to the 90th, a number with 90 zeros. This is in some sense beyond any cognitive handle. The mind cannot, in any meaningful way, hold this scale. We can write it down, we can compare it formally, but we cannot, in any subjective sense, feel its size. The vastness of cosmic time is, in some sense, one of the most striking features of modern cosmology. The cosmos has been around for 13.8 billion years. It will continue, in some form, for orders of magnitude longer. Our brief moment is, by every measure, a tiny slice. Yet we are here. We exist. We can think about all of this. We can model cosmic time. We can place ourselves within it. This is, in some sense, what modern cosmology has given us. The ability to situate ourselves in the long arc of cosmic history. We are not the centre. We are not the climax. We are one moment in a vast story. Second, the existence of heat death implies that the universe has, in some sense, a finite supply of useful energy. The cosmos is, in the early phase, energetically rich. There are temperature gradients. There are gradients of various kinds. These gradients can drive processes: chemical, biological, mechanical, computational. Over time, the gradients flatten. The energy becomes more uniformly distributed. The capacity for the cosmos to support processes, including any kind of life or intelligence, gradually decreases. This means that, even if we cannot directly experience heat death, it sets a kind of bound on what is possible. Life, in the standard physical sense, requires energy gradients. Life requires the universe to be in a non-equilibrium state. Heat death is the approach to equilibrium. Life becomes, in this picture, a temporary phenomenon, possible only during the early cosmic phases when the universe is still energetically rich. Third, the existence of heat death has implications for cosmological philosophy. It suggests that the cosmos has, in some sense, a particular history, with a beginning and an end. The cosmos is not eternal in any sense that preserves activity. The cosmos is finite in some meaningful way. These philosophical implications have been considered by thinkers throughout the 20th century, since the heat-death scenario became a serious and cosmological prediction. The implications are not, in themselves, scientific conclusions. They are reflections on what the science suggests. The reflections range widely. Some find the heat-death picture cosmically depressing. The cosmos ending in cold emptiness is, for them, a melancholy thought. Others find it strangely peaceful. The cosmos going through its natural cycle is, in this view, simply what cosmoses do. Different responses are valid. The science gives the prediction. The response to the prediction is, in some sense, a matter of individual disposition. Stay with me here. Let me also walk through what happens to specific cosmic structures during the long winding down. Stars, as I have indicated, gradually exhaust their fuel and die. Different stars have different lifetimes. Massive stars burn out quickly, in millions of years. The Sun, with its moderate mass, lives for about 10 billion years. Low-mass red dwarfs live for trillions of years. The longest-lived stars are the red dwarfs, with masses about a tenth of the Sun's. They burn hydrogen very slowly. They can sustain fusion for hundreds of billions of years, in some cases even up to 1 trillion years. After the Sun and other moderate-mass stars have died, the red dwarfs will continue to shine. Eventually, even the red dwarfs run out of fuel. When they do, they enter a brief subgiant phase, then become white dwarfs. The white dwarfs cool over very long timescales, eventually becoming cold dark objects called black dwarfs. The white dwarfs themselves contain some heavy elements. The carbon and oxygen in their cores is, in some sense, the legacy of stellar nucleosynthesis. As the white dwarfs cool, the heavy elements remain locked inside. Neutron stars, the remnants of more massive stars, also persist for very long timescales. They are extraordinarily dense, with masses comparable to the Sun, but radii of only about 10 kilometers. They cool slowly through neutrino emission and weaker electromagnetic radiation. Black holes, the remnants of the most massive stars, are even more extreme. They have no surface in any normal sense. They are defined by their event horizons. They cannot be entered and survived. Black holes evaporate by Hawking radiation. The smaller the black hole, the faster the evaporation. A stellar mass black hole, around 10 solar masses, evaporates in about 10 to the 67th years. A supermassive black hole like Sagittarius A star evaporates in about 10 to the 87th years. A really massive supermassive black hole, like the one at the center of M87, evaporates in about 10 to the 100th years. These timescales are, again, extraordinarily long, but they are not infinite. Eventually, all black holes evaporate. Eventually, the cosmos is, in some sense, empty. Now let me walk through what we have learned by considering the end of the universe. The work on cosmic end states has been, in some sense, one of the more speculative branches of modern cosmology. It involves extrapolating current physics to extreme regimes. It requires assumptions about future developments that we cannot, at present, verify. But the work has been valuable. It has clarified what our current theories predict for the deep future. It has identified specific scenarios with specific timescales. It has shown how different aspects of cosmology, stellar evolution, black hole physics, dark energy, combine to produce different end states. The work has also, in some sense, expanded our cosmological imagination. We can now think about the deep future of the cosmos with some specificity. We can compare different scenarios. We can identify what observations would distinguish them. This kind of long-term thinking is, in some sense, what cosmology gives us. The ability to consider, with some quantitative grounding, what the cosmos will be like in the very distant future. The future, of course, is uncertain. The scenarios depend on assumptions that may turn out to be wrong. New physics could change the picture. But the work has at least given us a framework for thinking about the possibilities. Hold this. Let me also walk through what the Big Rip would look like in detail. The Big Rip, if it occurs, would unfold over a particular timeline. In the lead up to the Big Rip, the expansion of the universe accelerates more and more rapidly. The rate of acceleration grows over time. Eventually, the rate of expansion exceeds the gravitational binding of various structures. The first structures to come apart are the largest. Galaxy clusters, held together by their mutual gravity, are torn apart as the expansion drives the constituent galaxies away from each other. The galaxies, no longer held in their cluster orbits, fly apart on the accelerating cosmic flow. After clusters, the individual galaxies are next. The stars within a galaxy, currently held in orbits by the galaxy's gravity, are pulled away from each other. The galaxy, in some sense, dissolves into isolated stars, drifting in expanding space. After galaxies, the planetary systems are torn apart. The planets currently in orbits around their stars are accelerated away. The solar system, as a coherent unit, ceases to exist. After planetary systems, the planets themselves are torn apart. The gravitational binding of a planet, which holds together its rock and gas, is overcome. The planet dissolves into smaller pieces. After planets, the atoms are torn apart. The electromagnetic binding of electrons to nuclei, which holds together atoms, is overcome. The atoms ionize and the electrons fly away from the nuclei. After atoms, the nuclei themselves are torn apart. The strong nuclear force, which holds protons and neutrons together, is overcome by the increasing expansion. After nuclei, the protons and neutrons might be torn apart. The strong force that holds together quarks within nucleons is overcome. The Big Rip, taken to its extreme conclusion, ends when no structures of any kind can exist. The expansion has become so dramatic that even quantum mechanical, bound states cannot persist. The cosmos has, in some sense, dissolved into nothingness. This is the Big Rip. It is, in some sense, the most dramatic cosmic fate. Unlike heat death, which is slow and gradual, the Big Rip ends in a rapid disintegration of all matter. The timeline for the Big Rip depends on the specific dark energy properties. Current observations marginally allow for the Big Rip, with timescales possibly tens of billions of years from now, or possibly far longer. The exact value depends on observations we are still refining. Now let me come back to the specifics of heat death. In the heat death scenario, the cosmos gradually winds down. Each phase has its own characteristic features. In the stelliferous era, the cosmos is, in some sense, lively. Stars form and die. Galaxies grow and evolve. Biological evolution, where it occurs, proceeds. This is the era we are currently in. In the degenerate era, the liveliness has subsided. The cosmos is populated by quiet stellar remnants. White dwarfs sit in their final forms, slowly cooling. Neutron stars likewise. Black holes accrete what little material remains. Biological evolution, if it has continued, has likely shifted to forms we cannot easily anticipate. The cosmos has, in some sense, settled. In the black hole era, the cosmos is even quieter. The black holes, which are the dominant remaining structures, slowly evaporate. The evaporation produces low-energy radiation. The universe is mostly empty, with the occasional drifting particle. In the dark era, the cosmos is essentially dead. The black holes have evaporated. The remaining radiation is so spread out that it cannot interact meaningfully with anything. The cosmos is, in the thermodynamic sense, at maximum entropy. This is the long arc. The cosmos goes through these phases. Each phase has its own timescale. The total span is, by every measure we can apply, extraordinarily long. Let me hold the question of what observers might exist during the various phases. In the current era, observers are biological. They depend on energy gradients and complex chemistry. They have limited lifespans. In the degenerate era, biological observers, as we know them, would have difficulty persisting. The energy sources, stars, have stopped functioning. The complex chemistry that biology relies on requires energy gradients that, in the degenerate era, are increasingly limited. But other forms of organization might be possible. Some researchers have speculated about observers based on the decay processes that occur during the degenerate era. White dwarf cooling, for instance, provides energy on a slow timescale. Whatever processes could use that energy could, in principle, support some form of organized activity. These speculations are, of course, speculative. We do not know if any form of complex organization can exist in the degenerate era. We know only that the conditions are different from the current era. In the black hole era, the situation is even more constrained. The dominant energy source is hawking radiation from black holes, which is extraordinarily slow and weak. Any form of organization would need to operate on timescales matched to this slow energy flow. In the dark era, no organized activity is possible. The cosmos is at maximum entropy. No gradients exist. No information processing can occur. So if there are observers in the late phases, they would be very different from us. They would, in some sense, be cosmic curiosities, exotic forms of organization that we can barely imagine. We are in this picture, observers of the early era. The era of stars, the era of complex chemistry, the era of biology. Whatever exists in later eras would be different. This is the picture, when we extend our thinking to include possible observers. Let me also walk through one more aspect of the late cosmos. By the time of the black hole era, the cosmos is, in many ways, drastically different from what we experience now. The galaxies have, in some sense, dissolved. The stars are mostly gone. The dominant phenomenon is the slow evaporation of black holes. In this era, the cosmic landscape is mostly empty. Vast distances separate the remaining black holes. Each black hole, evaporating slowly, is, in some sense, an isolated event in an otherwise empty universe. The evaporation of a black hole produces, near its end, an intense flash. The black hole gets smaller, hotter, and eventually emits a burst of high-energy radiation as it disappears completely. These flashes punctuate the cosmic darkness during the late black hole era. The flashes are, in some sense, the last cosmic events. After the black holes have evaporated, the cosmos enters the dark era, with no further significant activity. This is the projected sequence. The cosmos goes through the black hole era, with isolated, evaporating black holes, producing occasional flashes. Then the dark era, with no further activity. Then equilibrium. The total duration of the black hole era is, by current best estimates, from about 10 to the 34th years to about 10 to the 100th years. This is a vast span of cosmic history, longer than any preceding phase. Throughout the black hole era, the cosmos is, in some sense, in a long quiet phase, punctuated by occasional black hole evaporation events. The cosmic environment is sparse. The energy is, mostly, in low-temperature radiation. By the end of the era, even this is gone. The cosmos enters its final phase. This is the long picture. Stay with me here. Let me hold what this means for the question of cosmic meaning. If the cosmos ends in heat death, as our current best understanding suggests, then, in some sense, the cosmos as a whole has a finite duration of meaningful activity. The active phase, during which things happen, lasts approximately 10 to the 100th years. After that, the cosmos is in a state where no further evolution is possible. This is in some sense a finite story. The cosmic narrative has a beginning, a middle, and an end. The middle is by far the longest part, but it does eventually end. What this means for the meaning of cosmic existence is, of course, a philosophical question. Different thinkers have different answers. Some argue that the finite duration is itself meaningful. The cosmos has its time, and we are part of it. Others argue that the eventual death of the cosmos undermines any deeper meaning. The cosmos, in this view, is ultimately pointless. I do not, of course, have an answer to give. The question is beyond the science. The science gives us the prediction. Heat death. What we make of the prediction is up to us. This is the situation. We have a prediction. We have a long time scale. We have a particular kind of end state. We have our own subjective responses to all of this. The science is one part. The response is another. Now let me bring this closer. I want to walk through what the end of the universe says about our current moment. We are, in some sense, in a particular phase of cosmic history. The phase is the early stelliferous era. The cosmos is energetically rich. Stars are abundant. Galaxies are forming and evolving. Life, where it exists, can proceed. This is, by current best understanding, a relatively brief phase in cosmic terms. The total duration of the stelliferous era is approximately 100 trillion years. Of that, we have been around for the last 14 billion years. The vast majority of the stelliferous era is ahead of us, so we are early. We are at the beginning of what is, even by cosmic standards, a long, bright phase. This is, in some sense, a fortunate position. The cosmos is at its most vibrant during this phase. Things happen. Activity is possible. Whatever interesting cosmic phenomena exist, they exist now. By the time of heat death, in 10 to the 100th years, there will be very little happening. The cosmos will be quiet, no stars, no active galaxies, no much of anything. So our present moment is, in some sense, cosmologically privileged. We exist during the bright phase. We can experience cosmic phenomena. We can do science, we can build civilizations. This is perhaps what the end of the universe says about our present moment. Our moment is rare. Our moment is brief. Our moment is, in some sense, the cosmic equivalent of the early evening when the lights are still on. Hold this. Let me also walk through what the observable universe will look like during the various phases. Because the observational picture changes substantially as the cosmos ages. In the current era, we can see about 100 billion to a few hundred billion galaxies in our observable universe. The observable universe extends, in light travel distance, to about 13.8 billion light years in every direction. Within that volume, the cosmic web is visible. Filaments, walls, voids, galaxies in various configurations. As the cosmos ages and the expansion accelerates, the observable universe changes. Galaxies that are currently visible will, in time, be receding faster than the speed of light. They will effectively fade from view. By a few hundred billion years from now, most of the currently visible galaxies will have left our cosmic horizon. The observable universe will consist of only the galaxies that are now in the local supercluster, the ones gravitationally bound to us and to each other. By a few trillion years from now, even some of those local galaxies will have merged with each other. The local group will have become a single elliptical galaxy. The local supercluster will have similarly coalesced. Beyond the cosmic horizon, the rest of the universe is still there, but we cannot see it. The expansion has placed it beyond our ability to receive signals. For an observer in the very far future, in say 1 trillion years, the observable universe would contain only the local merged galaxy and a few other nearby objects. The cosmic microwave background would have redshifted to wavelengths we cannot easily measure. The picture of the cosmos available to such an observer would be dramatically smaller than what we have. This is one of the curious features of the heat-death scenario. As the cosmos ages, the observable universe shrinks. We are in some sense in a privileged position to observe cosmology. Observers in the far future will have access to much less. This shrinking observable universe is sometimes called the end of cosmology, in the sense that cosmological observation, as a science, becomes increasingly difficult and eventually impossible. The thought is, in some sense, a humbling one. We are not the lasting feature of the cosmos, we are not the climax. We are instead one expression of activity during the bright phase, before the long quiet that follows. But the thought is also, in some sense, focusing. We exist during the bright phase. We get to experience it. We get to do things. The cosmos, in its long arc, has produced this moment, and we are in it. This is the cosmic position. Brief, bright, embedded in a long, darker future. And importantly here, let me hold what this means for the values we place on our current existence. We are in a cosmic moment that, by every measure, is special. The cosmos is bright, stars shine, galaxies are active. Biological systems can exist. These conditions will not last. The bright phase will end. The cosmic conditions that support our kind of existence will, eventually, no longer obtain. But the conditions are here now. For us in this moment. Whether this makes our existence more valuable, or less, depending on which framework one applies, is a question that lies beyond the science. The science gives us the picture. The values we attach to it are our own. For my part, I find the picture both humbling and clarifying. We are in a special cosmic window. The window will close. While the window is open, we exist, we can think, we can feel, we can act. These activities are not, in any strong sense, eternal. They are features of our particular moment. The moment is, by cosmic standards, brief. But the activities are real. They happen. They have their content. They have, for us, their meaning. Whether the meaning is, in any deeper cosmic sense, lasting, is a question we cannot answer with science. Whether it is enough that the activities are real, now, even if they will not be later, is also a question we cannot answer with science. What science gives us is the awareness. We are in a bright phase. The bright phase will end. We exist now, in our particular slice of it. What we do with this awareness is up to us. Let me hold this awareness for one more moment. We exist in a cosmos that has a finite future. The future ends by current best understanding in heat death. The timescale is approximately 10 to the 100th years from now. We will not experience this end. Our species will not. Our planet will not. Even our galaxy, in any recognizable form, will not. But the end is real. It is, in some sense, where the cosmos is going. We are early in the arc that leads there. Knowing this changes nothing about our daily lives. We continue to live. We continue to act. We continue to do whatever we are going to do. But the knowledge is, in some sense, part of the picture in which we live. The cosmos is finite in time. In this sense, the cosmos has a beginning and an end. We exist in the long middle. This is the framework that current cosmology provides. We exist within it. We make of it what we make. That, in some sense, is enough. Stay with me here. Let me also walk through what happens to the cosmic microwave background as the universe ages. The CMB, as I have mentioned in other discussions, is the leftover radiation from the early universe. It currently has a temperature of about 2.7 Kelvin. The temperature decreases as the universe expands. By 1 billion years from now, the CMB temperature will be slightly lower than now. By 1 trillion years from now, it will be a fraction of a Kelvin. By 1 quadrillion years from now, it will be a tiny fraction of a Kelvin. The temperature continues to decrease, asymptotically approaching absolute zero. The CMB does not disappear. It continues to fill space. It just becomes colder and colder. The photons, redshifted by cosmic expansion, have less and less energy. Eventually, the CMB photons have such low energy that they cannot be distinguished from the thermal background of any detector. The CMB has, in some sense, faded into the cosmic noise. This is not a dramatic transition. It happens gradually over trillions of years. But it represents the slow disappearance of one of the major features of cosmic history. The CMB, our window into the early universe, becomes harder and harder to study. By the time the CMB temperature has reached 1/1,000,000th of a Kelvin, the radiation is essentially undetectable. We are, in some sense, fully in the dark era of cosmology. This is what happens to the CMB. It is part of the broader picture of cosmic winding down. Now let me come slowly to a quiet close for tonight. We have walked through the end of the universe. We have walked through 4 candidate scenarios: heat death, big rip, vacuum decay, and big crunch. We have walked through the most likely scenario, heat death, in detail. We have walked through the timescales, the phases, the processes. We have not, of course, arrived at a definitive answer. The various scenarios are, in some sense, all possible. Current observations favour heat death, but alternatives remain in the literature. The exact timeline depends on physics we are still working out. What we have is the picture. The cosmos has a finite future. By current best understanding, the future ends in heat death on timescales that are extraordinarily long. Let me hold one more aspect. The work on cosmic fate has, in some sense, a particular kind of intellectual character. It is more than most science speculative. The predictions cannot be directly tested. The verifications, when they come, will be from indirect observations rather than direct comparison. But the work is still science, in the sense that it follows logically from current physics and observations. The extrapolations to the future are based on theory that has been verified for current and recent epochs. The extension to the future, while uncertain, is principled. This is, in some sense, what science can do at its limits. We have theories. The theories make predictions. The predictions can, in some cases, be extended to regimes we cannot directly test. The extensions are speculative, but they are not arbitrary. For cosmic fate, the extensions are particularly extensive. We are projecting the cosmos's future for, in some scenarios, hundreds of orders of magnitude beyond the current age. This is unprecedented in any other branch of science. The fact that we can do this at all is, in some sense, a triumph of modern physics. We have theories of enough power and generality that we can ask and partially answer questions about the extremely deep future. The partial answers are what we have walked through. The cosmos, by current best understanding, ends in heat death. The timescale is approximately 10 to the 100th years. The alternatives are possibilities but not preferred. This is the answer. This is what we have built up through generations of work on cosmology. We are beneficiaries of all this work. We inherit it. We extend it modestly with our own observations and analyses. The work will continue in turn, with future generations refining the picture. We do not, in any individual generation, settle these deep questions. We contribute, we pass on. The cumulative picture, over time, becomes clearer. This is the texture of working on cosmic fate. Slow, speculative, cumulative, but progressing. Let me hold one more aspect of how this work fits in the broader cosmological enterprise. The work on cosmic fate is, in some sense, the long-term mirror of the work on cosmic origin. We have extensive work on the origin of the cosmos. The Big Bang theory has been developed in detail. We can describe with quantitative precision what happened in the first fractions of a second, in the first minutes, in the first hundreds of thousands of years. The early universe is, in some sense, well understood. We have extensive work on the present state of the cosmos. Observational cosmology has mapped the cosmic structure in detail. We know the parameters of the standard model with high precision. We understand how the cosmos has evolved up to its current state. The work on cosmic fate completes the picture, in some sense, by extending the description forward. The cosmos has an origin, Big Bang, a present, now, and a future, heat death. The full arc, by current best understanding, is laid out. This is perhaps one of the more impressive achievements of modern cosmology. We have, in some sense, the full picture of cosmic history, from beginning to end, on cosmic timescales. The picture is, of course, incomplete in many ways. We do not understand dark matter. We do not understand dark energy. We do not understand inflation. We do not understand many of the details, but the broad outline is there. We can see in our picture the long arc of the cosmos, from the hot, dense beginning to the cold, dispersed end, through the bright phase in the middle. This is what cosmology gives us, the ability to hold in our minds the full cosmic story. We are part of that story. We are in its middle. We are aware of it. That awareness is, in some sense, what we have walked through tonight. This is what current physics suggests. Let me hold one more thread. The work on cosmic fate has had, in some sense, a particular intellectual history. The earliest serious work on cosmic fate dates from the mid-20th century, when cosmologists began to seriously consider the long-term implications of the Big Bang model. In 1997, Fred Adams and Gregory Laughlin published a landmark paper, A Dying Universe in Reviews of Modern Physics. The paper laid out, in detail, the various phases of cosmic evolution from the stelliferous era through the dark era. The paper has become, in some sense, the standard reference for cosmic fate calculations. Adams and Laughlin used existing physics to extrapolate the cosmos's future. They calculated specific timescales for various processes. They identified the dominant phenomena in each phase. The cumulative picture, in their paper, is what I've been walking through tonight. Their work has been refined since. Subsequent researchers have added details, corrected estimates, considered additional scenarios. The Big Rip, for instance, was articulated in 2003 by Caldwell, Kamionkowski, and Weinberg. The vacuum decay scenarios have been refined as we have learned more about the standard model parameters. But the broad picture from Adams and Laughlin remains intact. The cosmos has a long arc. The arc passes through specific phases. The phases have specific timescales. The end point is, by current best understanding, heat death. This is the cumulative work of cosmology on the question of cosmic fate. It is, in some sense, one of the more developed branches of theoretical cosmology, despite the fact that it deals with predictions that cannot be directly tested. We are beneficiaries of all this work. We have a fairly detailed picture of what current physics says about the cosmic future. The picture has been built up over decades by many researchers. That is what we have inherited. That is what we are walking through tonight. If you have come here to rest, let this carry you. The end of the universe is, in cosmic terms, very far away. It does not threaten anything we know. It is, in some sense, the long, quiet outcome of the physics that governs the cosmos. The cosmos goes on. We sit in our brief moment. The end is far. The present is here. Let me hold one more aspect of the long arc. The cosmic timescales we have been discussing are, by every measure, vast. They exceed the duration of human civilization by factors of trillions. They exceed the lifetime of our species by similar factors. They even exceed the lifetime of our planet, which will be destroyed in the sun's red giant phase in about 7 billion years. So the end of the universe is not, in any practical sense, relevant to us. It is a feature of the deep future. We will not experience it. Our biological descendants, if any, will not experience it. Whatever form of organization might persist in the very far future would, by then, be utterly unlike anything we are familiar with. This is, in some sense, a comforting realization. The end is far. The end does not touch us. It's not. The cosmos's eventual fate is an abstract feature of the deep future, not a concern for our present. But the realization also points to something interesting. The cosmos's eventual fate, while not immediately relevant, is a feature of the picture in which we exist. We are embedded in a cosmos that has a particular trajectory. The trajectory has its endpoint. The endpoint is in the unimaginably distant future. We are, in some sense, in the early days of a long story. The story has its arc. The arc ends in heat death. We are at the very beginning of the arc. This is the picture. This is our cosmic position. Let me hold one final aspect. We are doing this work of cosmic fate prediction. In our brief moment of cosmic time, we have only had the theoretical framework for a few decades. We have only had the observational tools for slightly longer. In the deeper history of the cosmos, there were no observers asking these questions. The cosmos went through its early phases without any awareness. The first stars formed without anyone watching. The first galaxies assembled without anyone watching. Then, in some sense, observers emerged. Our species, and possibly others elsewhere, developed the capacity to think about the cosmos. We began to ask the deep questions. The capacity is, in some sense, recent. By cosmic standards, very recent. It is, in some sense, a privilege of our particular moment. The cosmos, in our era, has produced observers who can think about its own fate. What we do with this capacity is, again, up to us. We continue to ask, we continue to investigate. We continue to think. The questions are deep. The cosmos is vast. The work is ongoing. Let me hold one last image. Right now, in our particular moment, the cosmos is bright. Stars shine throughout our galaxy. Galaxies cluster across the observable universe. The cosmic web extends in every direction. Activity is everywhere. In 100 trillion years, this will not be the case. The stars will have stopped shining, the galaxies will be dim, the cosmic landscape will be very different. In 10 to the 100th years, even the dim remnants will be gone. The cosmos will be empty, in any meaningful sense. The heat death will have arrived. This is the trajectory. From our bright moment, through the long winding down to the eventual empty equilibrium. We exist at the beginning of this trajectory. We can see through our models where it goes. We can model the long arc. We can predict the eventual end. This capacity is, in some sense, what we have built up. Through generations of work, we have constructed the picture of cosmic fate. The picture is, by current best understanding, heat death. The timescale is vast. The end is far. But the end is real. We continue. The work, the thinking, the modelling, the observing. All of it continues. We are, in some sense, observers of our own cosmic situation, doing what observers can do. Let me hold one more aspect of the long arc. The cosmos, in its various phases, has gone through dramatic transitions. The transition from the early hot dense state to the cool expanded state we now inhabit. The transition from radiation-dominated to matter-dominated to dark energy-dominated. The transition from the first stars to the modern stellar populations. Each transition has its own characteristic time. Each marks a major change in the cosmic environment. The future transitions will be similarly significant. The transition from the stelliferous era to the degenerate era. The transition from the degenerate era to the black hole era. The transition from the black hole era to the dark era. Each will, in its way, change the cosmos fundamentally. The cosmos will be different after each transition. The capacity for various phenomena to occur will change. For life and intelligence, the transitions are particularly relevant. Life depends on energy gradients. The energy gradients diminish over time. By the late phases, the gradients are essentially gone. Life, in the form we know it, becomes impossible. This is one of the implications of the long arc. Life is a temporary phenomenon. It exists during the early phases when the cosmos is energetically rich. It cannot persist into the later phases when the cosmos has wound down. We are in this picture, in the early evening of cosmic time. The cosmos is still bright. Life is still possible. The energy gradients still exist. Let me hold this image. The cosmos in its current state is rich with phenomena. Stars are forming. Planets are forming. Atmospheres are forming. Life is forming, in at least one place we know of. These phenomena are, in some sense, the products of the early universe's specific conditions. The universe was hot. It cooled. It produced gradients. The gradients drove processes. The processes produce complexity. We are, in this sense, embedded in a complexity-producing cosmos. The cosmos is, in the bright phase, capable of producing the kinds of structures that we know. This will not always be the case. As the cosmos winds down, the capacity for producing complexity will decrease. The gradients will flatten, the processes will slow, the structures will decay. By the late phases, the cosmos will no longer support complexity in the way it does now. The bright era will have ended. We are, in our particular moment, in the productive phase of cosmic history. The phase is, by cosmic standards, long. It will eventually end. But it is here now, and we are within it. This is, in some sense, our cosmic position. Early in the productive phase, capable of complex existence, embedded in a long arc that begins and ends. Let me hold one more aspect. The cosmos, in its current state, is, in some sense, ours to investigate. We have built the instruments. We have developed the theories. We can ask the questions and make progress on the answers. This capacity is, in some sense, what makes our moment distinctive. We exist in a cosmos that is, at our specific moment, accessible to scientific investigation. The cosmos is, in our era, transparent to careful observation. This will not always be the case. In the far future, the cosmos becomes less transparent. The cosmic horizon shrinks. The structures dissolve. The observable universe diminishes. But we are here now, in the era when investigation is possible. We can see the cosmic microwave background. We can see distant galaxies. We can model the cosmos's history and future. We have, in some sense, an unparalleled view. Future observers, if any, will have less. The cosmic neighborhood will be more isolated. The observable universe will be smaller. The data available will be poorer. So we are, in some sense, in a particularly fortunate cosmic moment. The cosmos is, for us, open. We can study it. We can understand it. This is perhaps one of the privileges of our particular cosmic era. Let me hold one more aspect. The work we have walked through tonight is, in some sense, characteristic of how cosmology approaches deep questions. We have considered scenarios. We have weighed evidence. We have acknowledged uncertainty. We have laid out the most likely outcome. This is the methodology. It is not in itself definitive. It is, however, principled. We use our best current understanding to draw the best current conclusions. We hold those conclusions tentatively, knowing they may be revised. For cosmic fate, the methodology gives us heat death as the leading prediction. Alternatives are possibilities, but they require additional speculative assumptions. Heat death is the most economical extrapolation of current physics. We continue to refine the prediction. New observations may shift the balance. New theoretical work may identify previously unconsidered scenarios. The picture slowly evolves. For now, the picture is: heat death is the most likely cosmic fate. The timescale is approximately 10 to the 100th years. The cosmos winds down gradually. The activity ceases. The cosmos approaches its thermodynamic equilibrium state. This is what we have built up. This is what we work with. What lies beyond, if anything, we do not know. Let me hold one more thought before we close. The cosmic fate, as I have presented it, may sound bleak in some interpretations. The cosmos ends. The activity ceases. The complexity dissolves. But the bleakness is, in some sense, our interpretation. Not a feature of the science. The science gives us the prediction. The bleakness or hope or peace is what we attach to it. For my part, I find the picture, in some sense, more focused than bleak. The cosmos has a finite span of activity. We are in that span. We can experience the activity. We can think about it. We can do what observers can do. The eventual end does not diminish the activity. The activity has its own value, in its own time. The fact that it will eventually end is, in some sense, a separate question from its current reality. Different listeners will, of course, react differently. The science is the same. The interpretation is yours. What we have walked through tonight is, in some sense, what current physics tells us about cosmic fate. The picture is the picture. What we make of it is, again, up to us. By the time these gradients have flattened, billions to trillions of years from now, life as we know it will no longer be feasible. Whatever forms of organization might exist in the late cosmos would be very different from anything we recognize. Let me hold what we have, in some sense, walked through tonight. We have considered the end of the universe in 4 major scenarios. We have walked through the timescales, the mechanisms, the physical assumptions, and the implications. The most likely scenario by current best understanding is heat death. The cosmos gradually winds down. Stars die, black holes evaporate. The cosmos approaches maximum entropy. The activity ceases. The alternatives, Big Rip, vacuum decay, Big Crunch, are possibilities that depend on specific physics. Each has been studied. Each has its own characteristic features. None is currently the preferred prediction. The timescales involved are vast. Heat death is about 10 to the 100th years away. Even the soonest of the alternatives, the Big Rip, is, at the soonest, tens of billions of years away. For our practical existence, none of these endings is relevant. We will not experience the end of the cosmos. Our biological descendants, if any, will not experience it. The end is far by every measure, but the end is real. The cosmos has, by current best understanding, a finite trajectory. We are early in this trajectory. The trajectory will eventually conclude. This is the picture. This is what we have walked through. Stay with me here for one more moment. The cosmos, in its long arc, has many features. The bright phase in which stars shine, the long winding down, the final emptiness. We are in the bright phase. We are early in it. The phase will continue for a very long time, by every measure we can apply. The final emptiness is far in the future. This is our situation. The work we do, the science we develop, the cultures we build, the lives we live. All of this happens during the bright phase. It is the time when things can happen. It is the time when the cosmos can sustain complex activity. Let me hold this for a moment. The bright phase, by current best estimates, will continue for approximately 10 to the 14th years. That is 100 trillion years. We have been around for the last 13.8 billion years. So the bright phase has, in some sense, just started. The cosmos is in its early bright phase. The vast majority of the bright phase is ahead of us. Many more stars will form. Many more galaxies will evolve. Many more cosmic events will occur during this long bright phase. We will not be there for most of it. Our species will likely not persist for trillions of years. Even our cosmic environment, in any recognizable form, will not exist for most of the bright phase. But other things may happen. Other forms of organization may emerge. Other observers may, in principle, look at the cosmos and ask the same questions we are asking. The bright phase is, in this sense, the cosmic window during which observers like us can exist. The window is, by cosmic standards, long. By our standards, it is unimaginably long, but it is finite. After the window closes, observers like us cannot exist. This is one of the deepest implications of the heat death scenario. The cosmos has a finite window for life and intelligence. We are within that window. The window will eventually close. What this means for the value of our particular moment is a question I leave open. The science tells us that we exist in a particular cosmic window. The interpretation of that fact is, in some sense, up to us. The bright phase is, in some sense, our home. The dark phase is the long future we will not see. We sit in our small moment, in our small corner of the bright phase. The cosmos around us is doing what cosmoses do. It is going through its long arc. It is, in some sense, just getting started. We watch, we measure, we model, we think about what comes next. Let me hold one more aspect. The work of considering cosmic fate is, in some sense, the work of considering the largest possible questions. What ultimately happens to everything? What is the long-term trajectory of all matter, all energy, all structure? These questions have been asked in various forms throughout human history. Religious traditions have given their answers. Philosophical traditions have given their answers. Modern cosmology, in the 20th and 21st centuries, has begun to give answers based on physics. The physics-based answers are, in some ways, more specific than the older answers. They give us timescales. They give us mechanisms. They give us alternative scenarios with different probabilities. But the physics-based answers are also, in some ways, less satisfying. They do not give us, in any direct way, meaning. They do not tell us what to do with the fact that the cosmos will end. They give us the prediction. We are left to figure out the interpretation. This is, in some sense, the limit of what science can provide. Science gives us facts and predictions. Interpretation and meaning are, in some sense, outside the scope of science itself. We can use the scientific facts to inform our interpretations. We can use them to make our personal and cultural sense of the cosmos. But the meanings we make are not, in themselves, scientific conclusions. The cosmos will end. That is what current physics suggests. What we do with that knowledge is up to us. Let me hold one more aspect. The work on cosmic fate has, in some sense, expanded the field of cosmology. Traditionally, cosmology has focused on the present state of the cosmos and on its history, back to the Big Bang. Cosmic fate work extends the focus forward, to the deep future. This expansion has been productive. It has identified new questions to consider. It has connected cosmology to thermodynamics in deeper ways. It has clarified the role of dark energy in the long-term evolution. The expansion has also raised philosophical issues, questions about the meaning of finite existence, questions about the value of activities that, on cosmic timescales, are temporary, questions about whether anything that humans do can matter in the very long run. These questions are not, strictly speaking, scientific. They are philosophical, but they are prompted by the science. The science gives us the prediction of heat death. The philosophy considers what that prediction means. Different traditions have engaged with these questions differently. Some find the heat death scenario clarifying. The cosmos has its time. We have ours within it. The temporal limits are simply features of existence. Others find it deflating. If everything ends eventually, what does anything matter? The cosmic significance of any particular action seems, in this view, diminished by the eventual end. I do not, of course, have an answer. The question is beyond the science. The interpretation is up to the listener. What the science gives us is the picture. The cosmos has a finite future. Heat death is the most likely outcome. The timescales are vast. What we do with this picture is, in some sense, our choice. That is what cosmology gives us. The ability to see, through our models, the long arc of the cosmos from beginning to end. The arc is, in some sense, what we have walked through tonight. Let me hold one more aspect. The work of cosmology, as I have walked through, has given us the ability to see the long arc of the cosmos. We can see through our models and observations what the cosmos was like in the past. We can see through our extrapolations what the cosmos will be like in the future. This kind of visibility is, in some sense, what makes modern cosmology distinctive. We are not limited to direct observation of the present. We can extend our awareness backward to the Big Bang and forward to the heat death. The cosmos, in its full temporal extent, is, in some sense, available to us. The availability is, of course, partial. The future is uncertain. The past, while better constrained, is also not fully known. But the broad outline is, by current best understanding, clear. We are, in this sense, observers of the cosmos in its long arc. We see, in some sense, the full picture, even if we cannot directly experience most of it. This is, in some sense, a remarkable capability. The cosmos has been here for 13.8 billion years. It will be here in some form for vastly longer. We have, in our small recent moment, learned to see the whole long arc. What we do with this seeing is, again, up to us. Let me also hold the question of whether there might be cyclic or repeating cosmic histories. Some cosmological models, going back at least to the early 20th century, have proposed that the universe goes through cycles. In a cyclic cosmology, the universe expands, then contracts, then expands again, indefinitely. The simplest version of cyclic cosmology was the Big Bang followed by a big crunch, followed by another Big Bang, and so on. As I have walked through, the big crunch is currently disfavored, so the simple cyclic cosmology has lost ground. More sophisticated versions of cyclic cosmology have been proposed. Roger Penrose's conformal cyclic cosmology, for instance, proposes that the heat death state of one cycle is, in some sense, the Big Bang of the next cycle. The geometry is rescaled across the transition. Other versions involve bouncing universes, where the contraction does not produce a true singularity, but rather a transition into a new expansion phase. These cyclic models are at present speculative. They are not strongly supported by direct evidence. They are not strongly excluded either. If a cyclic cosmology is correct, the cosmos has, in some sense, no ultimate end. Each cycle ends in heat death, or similar, and a new cycle begins. The cosmos is, in some sense, eternal. But within each cycle, The experience of observers is similar to what we have walked through. The cycle has its bright phase. The cycle winds down. The bright phase ends. So even in cyclic cosmology, the heat-death scenario applies in some sense to each cycle. The difference is that the cosmos as a whole, across many cycles, persists. Whether the cosmos is in fact cyclic, we do not know. It is one of the open questions. Let me hold one more aspect of the cyclic possibilities. If the cosmos is in fact cyclic, then the heat death we have been discussing is not the absolute end. It is, in some sense, just the end of one cycle. What this means for our cosmic position is, perhaps, slightly different. We are not at the early end of a finite cosmic history. We are in one cycle of an indefinitely repeating cosmic process. Our particular cycle has its bright phase and its winding down. The next cycle, if there is one, will have similar phases. Whether cyclic cosmology, if correct, gives any deeper meaning to our existence is, again, a philosophical question. It does in some sense suggest that the cosmos is more enduring than the single cycle picture indicates. But each individual observer's experience is still confined to one cycle. So the cyclic picture, while interesting, does not directly change our experience. We exist in our cycle. The cycle has its arc. The arc ends in some form of winding down. Whether new cycles follow, we cannot, from within our cycle, directly observe. We can only speculate. We can only build theoretical models. The cyclic models, at present, are not strongly supported by direct evidence. They are not strongly excluded either. They sit in the literature as possibilities. For the most part, we work with the picture of a single cosmic cycle. The cosmos started in the Big Bang. The cosmos will end, by current best understanding, in heat death. The bright phase in which we exist is in the middle. This is the working picture. Whether it is, in fact, embedded in a larger cyclic structure, we do not know. We continue to investigate. Let me hold one more aspect. The work of cosmology, when extended to questions of cosmic fate, is, in some sense, the work of extrapolating present physics to extreme conditions. We take what we have learned about the cosmos in its current state and ask what it implies about the future. The extrapolation is, of course, uncertain. New physics could change the picture. Effects we have not yet measured could become important. The future is, in some sense, a place where our current theories may not fully apply, but the extrapolation is also our best current tool for thinking about cosmic fate. We do not have better methods. We have the physics we have learned. We have the observations we have made. We use these to project the future as best we can. The projection gives us heat death as the most likely outcome. The alternatives, big rip, vacuum decay, big crunch, are possibilities with varying degrees of likelihood. Heat death is the central prediction. This is what current cosmology tells us about the future. The cosmos, by current best understanding, ends in heat death over a timescale of approximately 10 to the 100th years. If new physics is discovered, this could change. The actual timeline could be different. The actual end state could be different. We continue to investigate. For now, the picture is what I have walked through. The cosmos has a long, bright phase. We are early in this phase. The long, dark phase follows. The whole sequence ends in heat death. This is the picture. This is what we have considered tonight. Let me hold for a moment what kinds of observations might, in principle, change our picture of cosmic fate. The future scenarios depend on physics that we are still investigating. Specifically, the nature of dark energy is critical. Various future experiments are designed to constrain dark energy with much higher precision than we currently have. The DESI survey is producing data over the next several years. The Vera Rubin Observatory will begin its full 10-year survey in 2026. The Euclid mission, launched in 2023, is providing data on dark energy through gravitational lensing. Each of these experiments will improve our understanding of dark energy's nature. The improvements will, in time, constrain the equation of state parameter W more tightly. They will tell us whether W is exactly -1, cosmological constant, slightly above, quintessence, or slightly below, phantom. If W is found to be exactly -1, heat death is confirmed as the prediction. If W is found to be different, the picture changes, either toward a slower or faster evolution depending on the sign of the deviation. These observations are, in some sense, what will resolve the picture of cosmic fate. We will, over the next decade or two, know much more about which scenario applies. The picture will become more specific. Other observations could also matter. Direct detection of dark matter could, indirectly, inform our cosmological models. Improvements in CMB measurements could constrain various aspects of the early universe and, by extension, the late universe. The work continues. We will, in time, have a much clearer picture of our cosmic fate. For now, the picture is what current best evidence suggests: heat death, on timescales of approximately 10 to the 100th years. The alternatives are possibilities but not preferred outcomes. We continue to observe. We continue to refine. The picture slowly sharpens. Let me hold one more thought. The work on cosmic fate is, in some sense, an exercise in humility. We are working at the limits of what science can know. The far future is, in some sense, beyond direct observation. Our predictions are extrapolations. But the humility is, in some sense, productive. Acknowledging the limits of our knowledge does not mean we give up. It means we work with appropriate care. We extend our theories. We test them where we can. We acknowledge the uncertainties. The result of this careful work is a picture, however incomplete, of the cosmic future. The picture is, by current best evidence, heat death. The alternatives are possibilities. The matter is being investigated. This is what we have at the close of tonight. A working picture, a continuing investigation. The questions are deep, the answers are partial. We continue. Thank you for staying with me through this story.